We're going to talk about some more graph terms now. So I'm going to kind of revisit some more concepts, things I've alluded to near the beginning of our lesson. So first thing I'm going to define is something called a path. I must stress that some people have different terminology for some of these things. So be warned, I'll try to give you some tips on how to distinguish between the two. But a path is simply a sequence of adjacent vertices. And some people call this a walk, to be very clear. So a path is simple. So some people call it a simple path. It's simple if all the vertices are distinct, meaning that they don't repeat. So one thing I want to bring up as an important remark is some people will refer to this as a walk, and some people will refer to the latter as a path. It's very common that when you talk about a path, usually it's this case that it is simple, but just be very careful and make sure you read carefully what they're talking to you about, if you need to know that distinguishing remark. So a path might mean just simply a sequence of adjacent vertices, or it might be a simple path if no vertices repeat each other. But you'll find in a lot of CS circles that the latter part is what people call a path. It's usually just presumed to be simple. So let me give you an example. I'm just going to draw out a graph here. So I'm going to draw something called a wheel graph. So you first start off with something called a star graph. They call it a star because you have a center to it, and then it has rays that go out of it, like a bright sun, you know, like a star, twinkles. So this is a star graph, and what I'm going to do is I'm going to make it so it looks like a wheel. So I'm going to add an outer perimeter, a pathway around the outer perimeter. This is what we call a wheel graph. So this is an example of it's just a graph, remember. So I'm just going to give these names. So V1 is going to be the center there, V2, and then I'm going to go around V3, V4, V5, V6, and V7. So suppose that I were to take some pathway in here. I'll include some other examples in the notes, but suppose I go from V7 to V2, down to V3. This is a path, right? Like V7 to V2 to V3, right? So I have V7, V2, V3. There's a path for you, right? It's a sequence of adjacent vertices. If I were to tack on V5 right after V3, is it still a path? No, right? It's because V5 is not adjacent to V3. But is this a simple path? Yeah, it's simple. Notice there's no repeating vertex. However, if I continue this pathway, I go to V1, then I go to V2, and then I go back to V7. Is that a simple path? No, because I've now repeated V2. So I must stress that you can also define for a directed graph a directed path. In that sense, you have to follow the arrows. So if there was an arrow, say from V7 to V2, then you can follow that arrow in your directed path, but you could not go the other way around. You actually have to follow the arrows. Just think of it like you're going on an obstacle course, but you're only allowed to follow the arrows. You have to follow the arrows. You can pick a direction to go in for your path, but you cannot go backwards on an arrow. That's the notion of a directed path. So it's also a concept of a cycle. So it's a sequence of adjacent vertices. So you know it's a path, right? But the first and last vertex are the same. So some would call this a closed path. So it means that you're taking some trip in the graph, but you have to, wherever you start, you end there. So for example, let's consider going from V6. Let's go V6, V7, V1, V6. This is a cycle, right? It's a path, but notice the start and end are the exact same vertex. So in this case, V6, V7, V1, V6, this is a cycle. And likewise, we can also define a simple cycle by the same rules. So it's called simple if no repeated vertices. Except for the last two, right? In particular, it has to be that these are at the start and end. You can't have it, for example, where it's just like somewhere going back to the start or the end, in between somewhere. It has to, what I'm saying is that you can have it where you can go from V6, V7, V1, V4, V5, V1, and then back to V6. That is a cycle. However, it's not simple because I repeated V1 twice. But notice V1 is not the start or end of the path. So these are the notions of a path and a cycle. You can also define the notion of a directed cycle on a directed graph by the same concept. So that being said, we're going to talk about some more structures that can exist with graphs. So let's talk about this. So you may have heard of this concept. If not, that's okay. Of the concept of a tree. Now, I'm not talking about trees outside. I'm talking about this notion of a tree that sometimes appears in some data structures classes. It's a very powerful concept because there's a lot of things we understand about the graph theoretic structure of a tree. Trees. So next we're going to talk about trees, forests. We're also going to talk about subgraphs and connectivity next. So first I thought I would start off with the last one, like what it means for a graph to be connected. So a graph is connected so we say a graph is connected if there exists a path from each vertex to every other vertex. To every other vertex. So for example, is this graph over here connected? I'll give you a moment to think about it. Well, let's look at any one of the vertices here. So I pick off V7 here. Well, V7, notice there's a path from V7 to V2, right? Through this edge. We can take that path. There's several other paths too. I can get the V1, I can get the V6 directly. They're part of my neighborhood. We're up in here, okay? So then I could also get the V5. For example, I'll take this path. I can also get to V4 from this path. That's one possible path. The point is that it exists, right? It has to exist. Having multiple paths doesn't make any difference here, as long as at least one exists. Also, V7 can also get the V3. You'll notice that each one of these pathways I can also take to go from that vertex to V7, right? Does everybody see that? So you can make arguments similar to this, but you can check each one of these vertices against every other vertex, And you can see that this graph over here is connected. It's an example of a connected graph. So that's an example of a connected graph. So this graph over here is connected. Now, you might naturally ask, okay, so what does it mean if that is not true? So suppose that I had another vertex. Say V8 over here, and I have another vertex, V9 over here. Suppose there's two vertices. They have an edge where both their endpoints are V8 and V9. Notice that there is not a path from V8 to V7, nor is there a path from V9 to V1, for example. Either one of them, or even it could have just simply been V8 just sitting out here by themselves. Maybe they're just enjoying the rest of their day, having a relaxing time. This would not be a connected graph. We would say that this graph is disconnected. So there's no path here, right? There's no path to V1. This would imply that this graph would be disconnected if you had this happen. Because there does not exist a path. So naturally, when you have a directed graph, you can have a stronger notion of connected. So I'll put more details in the notes about this, but if you have a graph like that, when you start imposing directed edges, so if you have directed edges in your graph, there's two different notions. There is the structural property of an edge. I was about to get physical about it. If there's simply an edge where its endpoints are the vertices, then it doesn't make any difference if it's directed or undirected. So there's this notion of connected as in the sense of an undirected graph. This is called weakly connected in a directed graph. And then we have this other notion called strongly connected. That is where there literally has to exist a directed path from one vertex to every other vertex. And this has to be true for every one of the vertices. Just like this, except you replace everything we talked about with a path with directed path. So that's the notion of weakly connected versus strongly connected. Strongly connected requires you just take this definition, you put directed path right here. In a directed graph, if you want to just talk about weakly connected, you'd use the same definition here, except you take every directed edge, turn them into undirected edges. If there's multiple edges, you just contract them into a single edge. So you just flatten those parallel edges into one edge, and then you ask the question. So I'll include an example of what I just spoke about here. Now, the next thing I'm going to talk about is the concept of a tree. And I must stress that there's many definitions of what a tree is. So I must stress that you're going to look at my first definition. If you ever learned about trees before, you may have gotten a different definition. So I must stress that there's more than one. So a tree is simply a connected graph with m. Remember, m is the number of edges. It's going to have m is equal to n minus 1, where n is the number of vertices. It has this many edges. So where m is equal to n minus 1. But I must stress that there's several other ways you could define a tree, and all of them are useful in their own ways. I must stress that there's probably some graph theoretic proofs out there that will use one characterization of a tree, or even combine these to help you. So you'll start off with saying, oh, okay, there's this is what a tree is, and then you might use one of these alternate definitions to invoke a property. It's very common. This is also one of the reasons why trees are so useful when you start talking about data structures. There's a lot of things you could say about a tree. So any two vertices, so this is one thing, any two vertices in the tree, G, are connected by a unique simple path, meaning that you can take any two vertices in the graph and there is a unique simple path between them. So that's another way you can equivalently define a tree. So you know right away the thing sitting behind me right here, that is not a tree, right? Because just keep in mind, I haven't drawn you what a tree looks like what a tree can look like. So notice V2, notice I can go to V7 by just going through this edge, but I also could go to V1, then go to V7. So you know right away this is actually not a tree. You also know right away it's also not a tree because it has too many edges. It's connected, but it is not a tree. Another way you can also define a tree is that G is connected, so our graph is connected. But if any edge is removed, the resulting graph, which I'll call the induced graph, so this is the graph that you get as a result of removing this edge. The induced graph is not connected. So removing any one edge in the graph will disconnect the graph. So you clearly see you can't do that to the thing right behind me. You'll find another pathway. Now here's another one. This also will give you some helpful insight in what a tree will actually look like. G is acyclic. This means it contains no cycles. So if you're looking at what acyclic means, just look at the word. Acyclic. If the graph is cyclic, it contains at least one cycle. If it's acyclic, it means the absence of a cycle, right? So there is no cycles in this graph. And the number of edges is exactly equal to n minus 1. Now, keep in mind that there are some other things you can do with a tree. So note that for any tree, if you try adding an edge to it, then what happens is it actually creates a cycle. So I'll show you with the example in a moment. So that's also an actually handy property that you can think about for a tree. Sometimes it's important that you can tell the difference between what a tree is and what isn't a tree. One thing you can do to any one tree is that if you add an edge to it, its resulting graph will have a cycle in it. Have at least one. So let me draw you a picture of a tree. Okay, so let's see here. So here's an example of a tree. Here's a tree. Notice that you can pick up any one of the alternative definitions or my definition over there. And you can apply it and you can check that this is in fact a tree. So you'll notice that there are no cycles in this graph. But notice that if I were to add, say, an edge right here, notice it actually creates at least one cycle. It'll create one right here. And also count the number of edges. I have 1, 2, 3, 4, 5, 6, 7. I have 7 vertices. The number of edges is 1, 2, 3, 4, 5, 6. There's exactly one less. So notice that if I were to include one extra edge, you know it's going to be connecting another pair of vertices that already have some edge incident on them, but it's going to create a cycle like we talked about. But also notice that if I tried to remove any one edge in this graph, notice that if I take this edge out, notice it disconnects it. So then these vertices can't reach those ones over here. So that's what a tree is. A forest, however, is a set or collection of trees. So suppose you want just not one tree, you want many of them. A set or collection of trees. So I must stress that for any forest, the relationship between the number of edges versus the number of vertices is always going to be m is less than or equal to n minus 1. This is actually something I may have mentioned at some past point, where if you bound the number of edges, there's some possibility, there's some freedom for how the edges may connect with the vertices. So you'll notice very quickly that if I remove this edge, I end up with actually 2 trees. Do you see that? This would be an example of a forest. It consists of 2 trees. So for example, here's a cute example of a forest. Drawing the pretty pictures. So it says 1, 2, 3 trees here. This is just one vertex, but it is still a tree. This is actually, some people would call a single vertex like this just an isolated vertex, because it's sitting out there by itself. It's all lonely. It's isolated. Make sure you spend some time with your isolated vertices. Okay, everybody? So next we have this idea of a subgraph. So it's just simply a subset of vertices. A subset of vertices and edges that forms, as a result, a graph H. So just some other graph. So you're going to take some parts of the vertices and edges. As long as it forms a graph, we could call it a subgraph. So for example, if I give you this lovely picture of a graph, I'm going to start off by drawing its outer perimeter. And I'm going to connect all of these vertices. Finally, I'm going to do one of those tricks that, at least when I was a kid, like people used to always doodle these all the time. I'm going to draw a star here. I promise I'm not trying to summon the occult or something here. We're not getting some superpowers here that are super epic or something that listen, my point is if anything that after watching this, you're after there and you're having some bad luck, please don't blame it on me, okay? So I'm just having a little bit of fun with you guys, okay? So notice that if I omit the edges that are all incident on these vertices, I end up with the star here that's in the middle. So for example, a subgraph here would be if I take these 5 vertices and all of the edges that connect these ones. So if I take all of these edges, I end up with this graph right here. So if this is G, this is my subgraph H. Do you notice very quickly that I can't just simply like have a dangling endpoint on an edge? Like remember, an edge consists of a pair of vertices, right? You can't have it where like there's no vertex here. It has to be that there's a vertex there. That's why when I say it forms a graph is very important. You can't just take any subset of these edges without including the vertices that are necessary to have those edges. So one thing I'm just taking a moment just to think about this. One remark I can make is that some people talk about the notion of an induced subgraph. That is where if you take a subset of the vertices, so you take some of these vertices, and you ask, okay, so what would be the graph if I only included the edges from the original graph that are present only with those vertices in place? That's what we call an induced subgraph. So one last thing I'm going to define here before we get into representations is the idea of a connected component. Now at first this is going to sound a little bit weird, so please just stick around with me. So a connected component. So I'll first write out a definition for you, and then we'll kind of dissect it. a maximally connected subgraph. So there's a few things that are in here that we've learned that I want to kind of put together with this new word. So first, we know what a subgraph is, right? It's some subset of the vertices and edges that form a graph. We know it's connected, meaning that we know that there's a pathway that exists between any pair of vertices I pick in that subgraph, I guess. And then there's this idea of maximally. So I haven't talked about that. So let's talk about it now. Now suppose that I gave you just a connected graph. Like suppose I even gave you this tree over here. You would agree with me that if I were to look at this, if I excluded in my subgraph one of these vertices, I'd actually be excluding parts of my graph that actually do exist paths to it. Meaning that I could actually extend my graph by at least one edge and at least one vertex, right? So suppose I want to include as much that I can possibly reach from some path between any two pairs of vertices in my subgraph. So I pick some subgraph, and the question is, can I extend the subgraph so it includes more vertices? And if the answer is yes, then it is not a connected component. If I can reach more vertices or across more edges, I include these in this subgraph. And when I cannot no longer include any more vertices or edges, then I could call it a connected component. So just as a quick example, suppose I have the following graph. So notice if I picked any one of the vertices here, here, or here, notice that if I try to extend my subgraph, say I start off with a subgraph, it's just one isolated vertex. You'll notice that it's not maximal, right? I could perhaps include more vertices and edges. Notice that there's these ones right here. I could extend this. There could be more edges in my subgraph. So notice that I can keep extending out this subgraph until I've included these 4 vertices. Since these cannot reach these vertices over here, I would call this box right here a connected component. So how many connected components are there in this graph? Well, first, the graph is disconnected, so you know there's at least one connected component, right? If it is connected, and it's just like this tree over here, for example. This is one connected component. That's it. Every connected graph is just one connected component. Yeah, we have 3 here. We have 3 connected components. This one, and this one. So the way you can explore or obtain these is suppose you just start at some vertex and you try expanding out your search to see if you can include more edges. And when you can't do that anymore, then you have a connected component. And then you can see if there's more that exist in your graph. Pretty fascinating, right? So this gives you some pretty interesting terminology we can build upon. Pretty cool stuff, right?